Hello from Luxembourg. I'm Bob Lombore and I'm working at Luxembourg Space Agency. We have been supporting FDL now for many years, and we are doing this in the frame of the Space Resource.lu initiative, in which Luxembourg aims to contribute to the peaceful exploration and sustainable utilization of space resources for the benefit of humankind. Last year, the Moon for Good team used unsupervised machine learning to understand and extract valuable information from thermal measurements of the lunar surface and was able to produce some amazing results. Following that very successful challenge, we are very happy that this year again, together with FDL and their partners, we came up with another inspiring challenge on space resources. This year, the challenge consists in producing high-resolution maps of the permanently shadowed regions. We believe that these maps will be an important information to find the ice on the lunar poles and will contribute to a better planning of the future lunar surface missions. The polar ice is a very important space resource, as it might change space exploration forever. Once we know where it is and we learn how to use it, we can, for example, produce propellant for rockets or water and oxygen for astronauts. We are very excited to see those maps. Now, I'd like to introduce you the team.
Thanks, Sarah and Bob, for the introduction, and welcome everyone, and thank you for joining our presentation. My name is Ignacio, and on behalf of the Moon for Good team, we're very excited to introduce the results of our work this summer, in which we focused on applying machine learning to improve lunar maps that could help with the identification, localization, and prospection of water ice. Before I kick off this presentation, I want to quickly acknowledge our advisory team, Miguel, Dennis, and Alison, as well as our partners, Luxembourg Space Agency, Google Cloud, Intel, and NVIDIA. We're very thankful for your support. 2020 has been a challenging year, no doubt. On the bright side, as Eugene mentioned earlier, it's been a productive year for the space sector with very important missions and a lot of progress made. And this year also kicks off what will be a new era of space exploration with even more ambitious goals for humanity. So what's next? We're going to the moon, and this time for good. NASA's leading a new era of space exploration with plans to return astronauts back to the moon by 2024 through the Artemis program. However, NASA won't be alone in this endeavor. Together with international partners and the private sector, we will start the development of a permanent lunar outpost. This will pave the way for long-term scientific and economic activity on the moon, as well as for the first human missions to Mars. But in order to realize this ambitious goal, we're going to need to take advantage of the resources that we can find on the moon. Among those, the most important one is water. Water can give us new insights about the story of the moon and our solar system. From a practical standpoint, water can be used as life support for future astronauts. And most importantly, it can be broken down through electrolysis into hydrogen and oxygen to meet a variety of needs, including rocket fuel, which could enable interplanetary travel. So water gives us a new paradigm for future space exploration. With the planned impact of the Alcross spacecraft in 2009, we were able to measure, and for the first time confirm, that water exists at the bottom of the Cabeos crater near the South Pole. Several other studies have also found evidence that suggests that water is abundant at the lunar poles, potentially as much as 600 million metric tons, and in particular, within the so-called permanently shadowed regions, or PSRs, a term that you will hear many times in this presentation. Now, this animation shows the sun's illumination of a few PSRs at the lunar South Pole. We define PSR as a topographic depression, like craters, whose interiors never receive sunlight due to the moon's low axial tilt. And because of this, PSRs are some of the coldest places in our solar system, with temperature below minus 100 degrees Celsius. These conditions create cold traps for water molecules as well as for other volatiles. And that's what makes PSRs the target for the upcoming lunar missions in the search for water ice. To recap, we have some idea of where we can find water ice, but not with precision. We won't know for sure until we send a rover or astronauts to explore the region. And because we cannot see inside of the PSRs, we cannot correlate topographic features of the terrain with where we think this deposit might be. So this lack of visibility also makes it very hard for mission planners to design a traverse for lunar rovers, as we don't know where smaller obstacles and hazards might be on the way. And this is precisely what the results of our work is trying to unlock.
So let's journey into one of these permanently shadowed regions. Imagine being inside one of these PSRs. It's extremely dark, and it's one of the coldest places on the solar system. So how on earth can we see into these shadowed regions? Well, it turns out that light does actually enter these permanently shadowed regions. It's not direct sunlight, but it's light that's scattered from the surroundings. And with the help of NVIDIA and their 3D ray tracing, we were able to show that for this crater, which is the Shackleton crater on the South Pole, light does actually enter inside the crater, inside its permanently shadowed region, and it's scattered from the rims of the crater. The problem is, if we take a normal image of one of these craters, it's extremely dark. And what we have to do is increase the brightness of this image a long way down until we can start to see features and inside of this crater. The problem is, if we zoom into that image and we look at it, we can see a lot of noise in the image. And this is because of the very low levels of light that the camera is receiving. This is very similar to what happens on your phone. We've all done it. We've taken a photo in the dark, and then we've zoomed in, and we think it's a great photo, but it turns out to be really grainy and faded. And the same thing is happening on the moon. Here's where we come in. We designed 2 neural networks to remove noise in these images and improve their quality. The first network we call destripe network, and it removes stripes in the images that we just saw. The second network we call photon net, and this one targets the graininess and improves the resolution and removes that graininess look. Together, we call our software HORUS, or Hyper Effective Noise Removal Unit Software. What we've essentially done is design night vision for the moon. And here's the result. The first image that you can see is a raw image of one of these shadowed regions. The second is after we apply our destriping network, removing the stripes in the image. And the third is after our photon network, removing that graininess. And you can see, after applying our techniques, we're starting to see features compared to the raw image that we would never see before. Things like craters and boulders. We haven't just done it to this image, we've actually done it to many different permanently shadowed regions on the moon.
So you must be wondering now what we can do with these improved images. Well, the most significant application of our work is, as mentioned earlier, is better traverse planning. As you see here, improving the overall quality of the images can enable us to plan in advance, as there is no room for error within the PSRs. As you see here, our little rover, which could not go into the shadow regions earlier because of the lack of information, now equipped with the information based on our results, know in advance where the obstacles, the craters and the boulders are, and can avoid them. Another major application is the ability to count craters within the PSRs with higher accuracy, as you see in this result. Crater counting is significant as it helps us in estimating the ages of the PSR, which in turn correlates to the chances of finding the ice. The age of the PSR also provide valuable information on mixing of the soil within the PSR and the estimates of the depths at which the water ice can be found. We also tried to locate the L-Cross, the spacecraft instrumental in the discovery of water at the North Pole, at the South Pole. As you see here, the green dot represents the crash site, which we know from the radar and the trajectory data. But till date, we do not have any visual imagery that confirms the crash site within the Cabayas crater. So with our results, we tried to locate that. Although we are not 100% successful in spotting a crash site due to the lack of signal within the Cabayas crater, we could still improve on the local crater's features beyond the existing PSR Atlas images. And it would not be overstating that we got closer to finding the spacecraft and the crash site in the visual imagery than ever been done before. Well, right now, space and the moon are viewed as something far away, limited to astronauts and the space agencies. But in future, this will change. One day, we all will be able to go to the moon. Imagine waiting in a spaceport on the moon, waiting for your rocket back home to the Earth. Our work is just a very small step in that direction, in manifesting that vision. But as we all know, sometimes a small step can lead to a giant leap. Thank you.
Great, wonderful work, Moon for Good team. So I'm going to invite our panelists back up here. And for this commentary, I'd love to know what is one word that you would describe this presentation with and why? So to kick us off, I would love to have Scott.
Hey, so one word to describe this?
Yep, one word.
Night vision on the moon.
Cool, we'll hyphenate that. Yeah, we'll hyphenate it. Great, thank you, Scott. And Aaron, what's your word that you came up with?
I think foundational. And the reason I think of that is because of water is the foundation it's a foundational resource for life as we know it.
Great, thank you, Aaron. And Rodney?
So the qualifier that immediately comes to mind to me is, I think, a bit more subjective, and it's inspiring. I think the reason why is because of the way that this whole project was motivated for the peaceful exploration of the lunar surface, which I think is important, as well as the fact that although there's a long way to get there, it could potentially close the loop to support surface missions by robotic rovers. I think that's going to be critically important when we're talking about performing in situ resource utilization. So yeah, I'll leave it there.
Hey, sir, I mean, I'm with Rodney in the sense that just imagine what this could do, right? Because we always talk about AI as a tool of science. And these are the kind of tools that the first woman on the moon is going to be using as she's walking around the surface, right? So AI allows her to see where humans cannot see before. And I think, James is talking about, that's what AI does. It's a tool like the first telescope. And by taking the data that she does have, she can then see things that human eyes can't see. And that sort of augmentation makes space exploration just so fascinating now with AI as a tool. And just one example of what happens when you take that power of, which we use in Silicon Valley and you put in the hands of these genius scientists, and we're starting to see some of that magic happen here today.
I couldn't agree more. And I also feel like your work has been very inspiring. And so I actually am going to have us watch a very inspiring video that our partner Google Cloud has produced on featuring the last year's Moon for Good work as well to end out this session. So please play that video.